Turn it over to you now, Tris.
Thanks. Well, hello, everybody. I think we picked up a few more people since last month when we had to reschedule. So it's good to see everybody here. And I want to let you know that based on comments I had heard during various continuing ed sessions and a query of Extension Nutrient Management Advisors, I realized that there were a lot of phosphorus issues that needed to be refreshed in all of our minds, and also some research data that we needed to share so we had a better understanding of some of the more recent findings about phosphorus and how it behaves in the landscape. So that's essentially what our talk is today. It's kind of like Phosphorus 301. And here's what I'm going to do. We're going to spend a little bit of time talking about the phosphorus cycle and phosphorus behavior. This is as a direct request of some folks that said, we covered this a long time ago in fundamentals, but it sure would help if we reviewed these things again. So we're going to review them. I'm going to talk about how we measure phosphorus both in fertilizers, commercial fertilizers, and in organic sources. We'll talk about some of the terms and methods people use, so that when you read a bulletin or hear a talk, you'll have the background for understanding it a little better. And then again, based on queries and things that have come up in my conversations with people, we're going to look at some research data from Maryland and from nearby states that specifically address people's concerns. Now realize that there's a lot more we could talk about. There are a couple hundred articles just of phosphorus-related stuff in the Mid-Atlantic. So I really had to cherry pick this stuff here so that we could limit our talk today to something that would be only 50 or 55 minutes. We can always follow up next winter with Phosphorus 401. Okay, first of all, it is time to talk about the phosphorus cycle again if people think they're a little bit weak on it from not having looked at it over the years. And what I'm going to focus on right now is several things. We're going to talk about this component right here, which is pretty much what happens when we talk about phosphorus fixation. There are basically two ways phosphorus is fixed. It can be sorbed or adsorbed onto soil materials. This could be clay minerals, particularly the edges, or it could be the iron oxides. You see that aluminum oxides are here too, but in our soils we really don't have much aluminum oxide. We're dominated by the iron oxides. So we've got this sorption and desorption stuff going on here. You can also have fixation via precipitation with other things in the soil like soluble calcium, soluble iron, soluble aluminum as secondary minerals. All right. So when people talk about phosphorus fixation, they're talking about either this sorption, desorption stuff, or they're talking about precipitation of new minerals. Another thing I want to point out here is this information over here. A fairly recent EPA bulletin has indicated that in their opinion, 50 parts per billion phosphorus, total phosphorus entering a surface water is potentially eutrophic. So that's considered the environmental threshold. Now this isn't the only number out there. There's some older literature that says 10 parts per billion is the environmental threshold, but right now the number that's being accepted by EPA at least is 50. So in some of our discussions later today and some of the slides we'll look at, I'll be harking back to this particular point. Okay? So phosphorus fixation occurs right here. You add a phosphorus source, it goes into the soil solution, and it can be fixed by an interaction either with reactive surfaces or with dissolved material in the soil solution. Either one of those is considered phosphorus fixation. Okay, now this is a diagram from the old Brady and Weil when it was black and white. It's nice and clear. And essentially I want to point out that in our agricultural soils in Maryland, where we're probably between a pH of 5.5 and 6.5, our phosphorus fixation issues are right here. You can see that that is the point where you'll get fixation by oxides of iron, aluminum, or manganese, in our case iron. Unless our soils are very low in pH, we're not going to get that chemical fixation or new soil secondary mineral formation because the concentration of iron, aluminum, and manganese is only high enough to cause this problem below about 5.5. So this absorption onto oxides is really what we're dealing with in terms of phosphorus fixation in most agricultural soils in our state. This is a modification of a very nice diagram that showed up in the anniversary edition of the Soil Science Society of America a couple years ago. And what they tried to do was show how the various materials we talk about among the soil colloids, or the very small things in soil, are actually related to one another spatially. So let me show you that we have a couple things here. These gray platey things are trying to indicate where the clay minerals are, those phyllosilicate, layer silicate things like kaolinite or illite, and they are often stacked up. Right? Then we have organic matter, and that's shown by the brown stuff here. And organic matter is kind of slobbered over the surfaces. It kind of covers other materials with a superficially active material. And then the weakly crystalline iron oxides, sometimes these are called the amorphous iron oxides because they're not picked up by X-ray diffraction. They too tend to exist as coatings on other things. So you can see this particular cluster of minerals here, first of all, has some oxides coating it, and then some of those oxides are themselves coated by organic matter. Right. Then we have these star-shaped things. These are considered to be the crystalline iron oxides. This is what your newly formed weakly crystalline stuff might morph into with time as it reorganizes internally. And it too can have organic coatings on it. The fact that things can exist as coatings means that they probably have more surface area than they would if they existed as a discrete solid clump of stuff. So there's a lot of relevance to the fact that our iron oxides tend to exist as coatings and not necessarily as discrete particles in our soils. It increases the surface, and as I'm going to show you in a minute, it's the surfaces where things happen. All right, this is a diagram that comes out of the new phosphorus monograph that American Society of Agronomy published, and what it's trying to show you here is a surface of an iron oxide. This could be a coating or a discrete particle, okay? And where the mineral ceases, we have what we call broken edges, and there are in fact exposed oxygens at those broken edges. Okay, so we've got these iron oxide groups, and the mineral stops here. It's the surface. So what happens at those surfaces? Well, hydrogen ions can come over and associate with those surfaces, and we know about that from our discussions of pH-dependent charge. But something that can also come over and associate with these surfaces is something like a phosphate group. Sulfate groups and borate groups can do this too. So in this case, we have some phosphate groups closely associated with the surfaces of iron oxides, here, here, and here. And these are very closely associated. So these are held rather strongly compared to the phosphorus that's farther away from this coating. And this author preferred to call this strong chemisorption. Right? Because of the closeness with which it's being held, it's held relatively tightly compared to the phosphorus out here, which is associated with the surface, but it's through waters of hydration and phosphorus that's even closer to the soil surface. So these are going to be even more readily available and more likely to be in equilibrium and replenish the soil solution than these ones that are held rather tightly. More recently, people seem to understand, and this is based on a lot of work with scanning electron microscopes and some surface techniques that we have like Xanase. We seem to understand now, first of all, that even if it exists as a discrete particle, it's not a nice, regular, square or round thing. It has what we might call internal pore space or cavitation. And all of these areas represent active surfaces where absorption can happen. So if an iron oxide newly forms in the soil as a result of conditions in supersaturation, and these phosphate ions are out in the soil solution, they can associate with the external surfaces. And with time, they might also move into these surfaces on the cavities, or move into what we might call the internal surfaces. Now, obviously, all things being equal, these things that are on the outside are going to get bumped off and move back into the soil solution much more easily than something that's deep in a cavity or deep in a pore space in a porous iron oxide mineral. Okay, enough with our basic soil phosphorus chemistry. Let's talk about how phosphorus is measured in fertilizers and organic residuals. First of all, if something is labeled as a fertilizer, and I don't care whether it's a commercial inorganic fertilizer or a commercial organic fertilizer, if it is labeled, the phosphorus in that fertilizer is what's called available phosphoric acid, and it's the sum of what is water extractable and what's citrate soluble or citrate extractable. Now, for a lot of commercial fertilizers like MAP and DAP, the available stuff is 100% water soluble. But for some of our older forms of commercial inorganic fertilizer like single and triple superphosphate, that's not true. And for the organic fertilizers that are labeled as P fertilizer, that certainly isn't true. On the other hand, when someone reports the amount of phosphorus in a manure or an organic residual like a compost or food waste or something like that, that material has been subjected to what we call a total digest. Either very, very high heat or a very strong mixture of acids has been used to break down all the organic material in it. And the phosphorus that's released when that organic matter is broken down is measured in an acidic solution. All right? So it's actually a very, very different technique that we'd use to describe the total phosphorus in an organic material or a manure compared to the phosphorus that would show up in a fertilizer label. And in addition to that, as we'll see in one of the studies that we look at today, water extractable phosphorus, it has been suggested as a useful thing to know about in terms of the phosphorus in our organic residuals. There are several studies out there that show that it's not so much the total phosphorus in an organic material, but the water extractable or the water soluble phosphorus that really could give us a better idea of what's going on. And if we knew it about our various materials, might help us better predict phosphorus losses. And unfortunately, and I'm not going to show you that data today, there's at least one study that shows that water extractable phosphorus can vary quite considerably within a manure group. It can be quite different from poultry litter to poultry litter, quite different from dairy manure to dairy manure, depending upon how that material has been handled. It is not, however, a typical measurement that one could request of a lab that did manure testing at this point in time. But I think down the road it might become one of those things. Okay, now we're going to look at some runoff studies today, and that's certainly something of great concern in Maryland and something we try to sort of predict or account for in phosphorus risk assessment tools like the Phosphorus Site Index or the Phosphorus Management Tool. And you've probably all been to talks where someone's talked about phosphorus and runoff. So let's talk about the different forms phosphorus can exist in or be associated with, so that when you read those things or hear those talks, it makes more sense to you. First of all, people often measure the total phosphorus. All right, and they abbreviate that by TP, and that essentially is both the soluble and the particulate phosphorus. The soluble phosphorus is often abbreviated as DP or DRP, and it essentially is the phosphorus they can measure in the solution that comes through a 0.45 micron filter. Now, I've tried to find out why we use that particular size of filter, and I have to tell you, I have not gotten to the bottom of that yet. But it's a very, very fine filter. It basically, by definition, if it passes through that filter, it is soluble. People recognize that it might contain some very, very fine colloidal-sized stuff, but it's the best we can do. Then there's the particulate or the sediment phosphorus, often abbreviated as PP, and this is the phosphorus that's absorbed onto particles that are moving in that runoff. So you typically find both the particulate phosphorus and the total suspended solids measured in experiments, and that's abbreviated by TSS, and that essentially is the particles that are being carried off by the runoff, or what we would often call erosion. Right? So these are the common things people tell one when they're doing a runoff study. All right. Then there's the phosphorus in the soil. And there's a number of things that are now looked at to get a pretty good handle on what's going on in terms of the phosphorus in the soil. And the traditional soil test is certainly the most important one. We have a lot of data on that. So anything we can relate to a traditional soil test is going to be gotten more readily than expecting people to do an additional test to get more information about the environmentally important forms of phosphorus in your soil. Right? And of course, the dominant extraction in our region has become Malic-3. Even labs that did Malic-1 a couple years ago, 5-10 years ago, have switched to Malic-3 now. But another thing that's being looked at in research situations is the water-soluble phosphorus. This is essentially taking a certain amount of soil, mixing it in a certain amount of distilled water, and finding out how much phosphorus is extracted under those circumstances. And this is important because it's seen as a surrogate for the phosphorus that is in a form that it can leach readily or run off readily when water either moves through or moves over the soil. So again, while this isn't a typical soil test that's done by a soil testing lab, it is something that most researchers are doing now if they're doing phosphorus work. Then there's the new test that we've talked about in reference to the phosphorus management tool, and that's the degree of phosphorus saturation. And just to give a little bit more information on that, it may also be known as the phosphorus saturation ratio, and it essentially is telling you how much sorbed P you already have in that soil compared to that soil's sorption capacity. All right? Now, sorption capacity varies tremendously from soil to soil. Soil sorption capacity is related to the amount of clay and the kind of clay and the amount of oxides you have. And even within a state, or I would hazard to guess a county, the phosphorus sorption capacity is going to be pretty significant from one location to another. And essentially, in its purest form, in its original form, the degree of phosphorus saturation was calculated based on the oxalate extractable phosphorus divided by 1/2 times the iron and aluminum that one extracted in an oxalate extraction. And I will tell you that there's about 25 years of data, starting first in Europe, in Western Europe, and then being done in the United States on this particular test. And it's quite powerful in terms of giving us some information about whether or not our soils still can hold more phosphorus or whether they're already pretty filled in terms of their capacity. So first of all, I want to show you some relationships here, and this is some data that comes from Frank Cole's grad student, Jen Butler, that was done in the late 1990s and published in 2003. And they looked at the dissolved phosphorus compared to soil test phosphorus, and this was actually Malic-1, because that's what the lab was running then, on 4 different soils on which she conducted her research. And as you can see, there is an increase in soluble phosphorus or dissolved phosphorus as a function of soil test, but it's not a perfect relationship. These silt loam soils, the Mattapex and the Mattapeak, certainly exhibited much less of an increase in dissolved P with increases in Malic-1 extractable P, whereas the sandy loam soils, the Keyport and the Donnellan, had much more dissolved P. So it's not a perfect relationship. We know that as one increases, the other one does, but you certainly can't make much predictions of what's going to behave across the county or across the state when you have this much variability in your data. And another thing that Jen Butler did was look at the dissolved P as a function of degree of phosphorus saturation. And here's where things really get interesting. Notice that when the degree of phosphorus saturation is pretty low, up to about, maybe 20, 25, that there's very, very little dissolved P. And it's only after that point that things start to go up. And again, these lines converge a little bit better, not perfectly, but a little bit better than the relationship that we just saw when we only looked at the soil test P. And this led Dr. Cole and Jennifer to suggest that above a certain point, and this change point between we don't have a problem to things are starting to increase rapidly, happens right about at 20, 23, 24, 25, and it's at that point that we're willing to say these soils are high in P. They're not going to hold much more. If they're above this change point, they're in essence saturated, and that phosphorus is going to be environmentally labile. All right. Now, one comment that came up during the regulatory update in December was a comment by someone who was really amazed that our recommendations for phosphorus might actually be greater than the crop removal. So I'm showing this just to reinforce to us that in some cases we have soils that are very low in phosphorus. We probably have more of these in western Maryland than we do on the eastern shore, but we could probably find some on the eastern shore if we looked hard enough. And in fact, for 150 bushel corn yield goal, the removal would be 60 pounds of phosphate per acre, when in fact at an FIV of 10 and 20, we're recommending far more than that based on Maryland's recommendations. So I want you to think for a moment and see if you can give me a reason why our recommendations at these soil test levels are so significantly higher than the removal rate for that corn crop. So I'm going to give you about a minute here to come up with a reason or two why this might be the case. And Josh, while people are answering this question, I want to say that sorption is a very nebulous term. Adsorption with a D, ad, is from Latin meaning to. It means the adsorption is on the surface, whereas AB, ab, means that that material is being taken into a structure, or in the case of an organism, into an organism. So we often talk about absorption in terms of digestion, where stuff is being taken into our bloodstream, whereas if something's coming to a surface but not going into that material, it's adsorption, adsorption. Okay, as soon as people are done typing, we'll share information. Okay, well, let's look at this. If we've got an FIV or 10 or 20, these are soils that are probably pretty close to their natural unfertilized state. All right, maybe they've just been taken out of, I would say almost woods. Even unimproved pasture usually comes up higher than this. So these haven't had much exposure to phosphorus additions at this point in time. And it's pretty fair to say that in our climate with the iron oxides we have, due to the fact that our soils are relatively highly weathered compared to soils in other parts of the country, that there's significant phosphorus fixation capacity. And when a fertilizer is added to that soil, it goes into solution and immediately upsets the equilibrium and stuff starts happening. And one of the things that starts happening is soluble phosphate ions are adsorbed onto surfaces. All right? So some of that phosphorus that you just added is no longer in the soil solution where it can nourish your plants. It is, in fact, adsorbed onto surfaces and has been taken out of play for at least a period of time. And for that reason, if we want enough in that soil solution to nourish this crop at a very substantial yield goal, 150 is very good for most parts of Maryland, research demonstrated that we have to add more than is removed to compensate for what's going to be taken out of play during the phosphorus fixation reactions. So Phil, you hit that on the head. So did you, Ashley. Thanks very much for taking a stab at that. Okay, now here's one that's a huge concern right now. Apparently there's a very commonly held belief that if people, even with high soil tests, and the one person who called me had a soil test FIVP of 500, very concerned that there's not enough phosphorus in his soil. He's sure he gets a phosphorus response, and the soil test just does not reflect what's there for his crop at all. So I'm going to show you some data now to hopefully give you some information to deal with this kind of a comment or a notion. All right, first of all, we know that nutrient availability is a continuum. It's not a black-white. We don't have a certain amount available and another that's unavailable. In fact, with phosphorus and with a lot of other nutrients, there's some that's very readily available, some that's less readily available, some that's even less readily available. So down here we might have the stuff that's the phosphorus that's absorbed on the outside of surfaces on a newly formed iron oxide. Down here we might have newly precipitated iron phosphates. Back here we might have the stuff that's in cavities, has to diffuse out before it can be more readily available. Back here we might have stuff that's occluded or actually covered over by new stuff. So there's stuff that may be released over a growing season that exists in various forms in terms of immediately readily available and less readily available. So this A soil test that extracts this component down here might be something like the distilled water test that's used in the sandy and organic soils in Florida. And the B might be closer to a Bray or a Malic 1. And the C, which is an even stronger extractant solution, might reflect what's in a Malic 3. But the fact is they're all extracting plant available forms, all of them. And in order to use them validly, you have to couple them with the recommendation system that was developed alongside them. Okay? So let's talk about the Malic 3. It's been on the street since about 1981, at least used in North Carolina where it was developed. Malic was a North Carolina scientist. I believed he worked for the Department of Ag, not for the university. He'd already developed Malic 1. I'm not quite sure what his dissatisfaction was, but he developed Malic 2, which was only used for a couple of years before people realized it was tearing up their atomic absorption units. And so he went on to work with Malic 3. He was looking for what was called a universal extractant. He wanted something that could extract the macros and micros in acidic and neutral soils all in one extract. Realized that some soil test labs until very recently used a separate extract for phosphorus than they did for the bases, and then a third one for the micronutrients. And if you're trying to run a soil test lab, that's a lot of glassware, that's a lot of labor. So he was looking for one extract that could be used for everything. So he came up with Malic 3. Now here's what's in Malic 3, and it is in fact a mixture, or what I like to call a cocktail. It has EDTA in it. I'm not going to tell you what that means. If you want to know what that means, send me an email and I'll tell you. But this was used to extract the micronutrients. Right? The ammonium nitrate was used to extract the bases, calcium, magnesium, potassium. The ammonium fluoride was in there to displace adsorbed phosphate. It's a small anion, and it's quite effective at displacing or extracting that adsorbed phosphorus we talked about. And the mixture of acids was there to basically make a medium in which these other things, after they were extracted, wouldn't precipitate out with one another. So he found it. He found a fairly effective universal extractant. All right? There is no reason to believe that any phosphorus we get out of a Malic 3 with this ammonium fluoride is not in a form that is plant available. All right? There is simply no reason to believe that. Okay. Now, let's look at some data. This was a multi-state effort. There were 23 site years from the Mid-Atlantic and done in 98 and 99. The concerns that drove this study were the fact that with the amount of manure that was being used in this region, maybe our data on nutrient removal was archaic, and maybe we ought to look at that. And so sites were selected over a range of Malic 3 soil test values from about 50, maybe 40 or 50, up to 400. Corn was grown. I believe it did have starter the grain was harvested, and we looked at the phosphorus concentration in the corn grain expressed on a dry weight basis. And what we found was that, as a general rule, the higher the soil test level, we did see an increase in the amount of phosphorus that was actually in the grain. All right. Now, there's a lot of clustering down here, a lot of variability. You can see that even at some fairly modest levels where there might still be a recommendation, there was quite a range from 3 to 4 milligrams per kilogram. That would be 0.3 to 0.4%. But there definitely is a positive statistical relationship between Malic 3 soil test P and the amount of phosphorus that's actually in your grain. There certainly is reason to believe, or no reason to disbelieve, that out here at these higher soil test levels, we need more phosphorus. There certainly are very significant levels of phosphorus in those soils, or excuse me, in the corn grain, as well as in the soils. Okay, so now let's look a little bit at how phosphorus behaves. And we are fortunate to have one intensively studied watershed that is giving us some very valuable information. So let's look at it first. First of all, this is a watershed that's been intensively studied by the USDA Watershed Research Group up at University Park, Pennsylvania. I've not been fortunate enough to go on one of the several tours of this watershed, but it's small, it's confined, it's mixed, and they must have a very good relationship with the producer because they've got instrumentation all over this farm. First of all, these are the actual fields, and you can see that the white areas are actually managed cropland. There's also some forest land, and there's some pasture land. There's farm structures here, and there's essentially a stream that runs out of away from this property, exiting the watershed, and there is a flume at the outer channel, outer point of the watershed. So it's a small, intensively instrumented, intensively studied watershed. There's a lot of the work that's been done at a watershed scale and even a field scale has been done in this particular watershed, thanks to the group from USDA. Okay, so I want to tell you about one of the studies they published. All right, first of all, they have been monitoring the outflow of that watershed since the beginning. And the study I'm going to show you here was published in 2008, but it represented 10 years of monitoring data. And they literally take a sample at the outflow of this watershed every 5 minutes, all right? So they can tell what comes from storm flow, the water that flows in that creek after a storm, and what comes from base flow, all right? And they found that 32% of the total flow of water occurred as storm flow. So about a third of the water exiting that watershed in that little creek occurred during storm flow, leaving about 2/3 or 66% as base flow. But they found that 65% of the dissolved phosphorus and 76% of the total phosphorus leaving the watershed came during the storm flow. So the amount of phosphorus that's leaving, whether it's particulate or dissolved, is way out of proportion to the amount of water that's leaving. They concluded that large, infrequent storms have a potential to transport large amounts of phosphorus, okay? Not unlike other people have found, too, in this region. And here's an important thing that they found. They found that their base flow, the water that's flowing in that stream, is the result of having flown through the soil profile and then flowing laterally into the stream. The base flow was 60 parts per billion. Now, if you remember back to that earlier slide I showed you, EPA has established a eutrophication threshold of 50 parts per billion. So even the base flow coming off this watershed could potentially cause eutrophication problems in the streams that it impacts. Okay, well, it's nice to know what happens in a whole watershed, but sometimes we want to know what's happening in individual fields, all right? So in order to do that, we would need to collect the runoff and measure the phosphorus in it. And we'd need to measure the particulate as well as the soluble phosphorus because we know both of those are important. And this is doable, but you need basically a flume with a flow meter and a sampler. And those apparatus, the last time I priced them, ran about 20 grand per unit to purchase and install them. And these numbers are about 10 years old, so it's probably 25 or 30 now. And of course, we want more than one. We know that we want to look at different treatments, different soils are different soil provinces are different. So you'd want a bunch of these, lots of places. And then I just talked about the installation and the equipment. These would have to be maintained. People would have to make sure they're still working. And there'd be a sample cost to analyze your data involved. So we do have limited data on these in one or two places, but we certainly can't afford to put this kind of apparatus in all over the universe where we might want to know what's going on. And this is actually a picture of the apparatus that's monitoring a watershed over at the University of Maryland Y Research and Education Center. They have two watersheds where they can actually look at the outflow from these small areas. But they only have two. So we're looking at what is going on in basically one soil map unit with two treatments, no replication. And that just won't cut it in terms of wanting to extrapolate the information to the universe. All right. So people have looked at what I'll call surrogate measures. What do we have out there that's more flexible, less expensive, and allows us to look at a whole bunch of options, all right? Different soils, different physiographic provinces, different treatments, different pea sources, whatever. So I want to show you some of the surrogate measurements that we now have. And first of all, there's something called a plot-based runoff rainfall simulation, okay? We basically have apparatus called rainfall simulators. There's one kind of accepted model by many scientists in the U.S., and then there's some renegade systems out there that don't want to agree with anybody else. Anyway, they're all transportable. You can move them from field to field, site to site. You can look at multiple treatments in the same management unit. This is important if we want to compare anything. You can do up to 5 plots a day. That is, you can get the runoff measured on about 5 plots a day. It is definitely a job for more than one person. You can't send a grad student out here by themselves. It's got to be a team of people. And they did find, when they were out at Clarksville doing it, that these systems can become airborne on a day where you've got a little bit of wind. So here's a schematic of it. Essentially, you've got a pressure gauge because you're carefully metering the water here. Different scientists usually want different intensities of storm. Some want a 10-year storm, a 5-year storm, a 50-year storm. They haven't seemed to agree on the kind of storm they want to look at either. But they carefully have to know what their water pressure is. There's a frame that fits over this. It does have sides. There's a grid here that is going to make sure that the water that falls here is the water that's collected in these runoff vessels here. And they tend to divide it in half so that they essentially get 2 measurements per rainfall simulator. All right? And here's the one that's been used by a number of people in Virginia, Maryland, Delaware, and you can see it does have these sides here. Those curtains are there so that if there's a little bit of wind, the wind doesn't blow the rainfall away from the plot. It's all going to go down, all right? And herein lies the reason why it can become airborne. All right. Now, I'm going to show you a study from some work that was done at the site we just looked at. This is the University of Maryland, Central Maryland Research and Education Farm at Clarksville. They looked at phosphorus applications, and they looked at a fairly high application rate, 450 pounds of phosphate per acre. And that's what they assumed could be associated with a nitrogen-based application of sewage sludge. This research was funded by the Maryland Council of Governments to get some data on runoff of the various biosolids in the region. So they had a control where no phosphate was added, iron-stabilized biosolids, lime-stabilized biosolids, lime and iron-stabilized biosolids, and then poultry litter. All right? So let's look at some of the data that they could generate with a rainfall simulator. Now, it took all week to get the replicates of these 5 treatments. Right? And that's one thing that limits what you can do. You want to you want to get it done in about a week's time when you don't expect any rainfall, so that you don't introduce more variability, doing some plots having been rained on and others not. The treatments were incorporated, so all the biosolids and the poultry litter was incorporated, and the corn was planted immediately. All right. Thereafter, they practiced no-till. All right. The Chester silt loam was the dominant soil, and an 8% slope, and they added water. They added water through that system to get runoff for 30 minutes. They wanted 30 minutes of runoff. Now, they did this not only one day after they incorporated the biosolids, they also did it 1 month, 6 months, 12 months, 13 months, and 18 months. All right. Here's why they did it that way. The 1 month was supposedly after canopy closure. So at this point, your crop cover is protecting the surface. The 6 months is at harvest. Right. The 12 month is after planting year 2. 13 is after canopy closure year 2, and 18 months was after harvest in year 2. So they looked at the runoff over a significant period of time. And there's a really interesting data set. A similar study was done up in Delaware, and that's published, but this is some data from the grad student that actually did the work. All right. And so we've got the 1 day data, the 1 month data, the 6 months data, the 12 month data, 13, 18. We have total phosphorus over here on this axis, and then based on the color, the dissolved phosphorus is in the blue, and the particulate phosphorus is in the yellow. Okay? So look at this for just a moment and tell me some of the important things that looking at total, dissolved, and particulate phosphorus over time can be discerned from an experiment like this. I'm going to give you about a minute to provide some information on that. Okay, as soon as Trish is done typing, we'll share some information. Folks are pretty quiet out there. Particulate phosphorus is less, while dissolved phosphorus increases. Okay, yeah, a number of things. Okay, look at what's going on a day after incorporation, but look at how your total P drops over time as you switch from conventional to no-till. Here's a beautiful example of how we can reduce our phosphorus losses, our total phosphorus losses, when we go from conventional to no-till. All right. We can also see that under many circumstances, virtually at very many treatments at very many times, the particulate was greater than the dissolved. Okay, and that's a good question. How important is particulate phosphorus? How bioavailable is particulate phosphorus? Well, Andrew Sharpley, who's basically the father of soil phosphorus chemistry in America, basically has a study where he indicates, based on his work, and he's done more than any other single person, that the bioavailability of particulate phosphorus can be as low as 5% or as high as 100%. So it's very hard to predict with that kind of a variability how bioavailable this particulate phosphorus is. But we do know that it tends to be as much or more than the dissolved phosphorus in virtually every case. What I was really surprised at here is after canopy closure in year 2, the losses appear to be higher than they were after planting. That kind of boggles my mind. And also, there's not a huge difference here between these treatments in terms of what's dissolved. Personally, I was quite surprised at that. But the beauty of this technique is that it can give you these bits of information so that you can either confirm or dispel your operating principles as to how things behave. All right? Thanks, Tricia. Appreciate it. All right. So one of the problems with the simulation on plots is there's a limited number of variables you can study because you want to get all of your runoff done when the soil is essentially in a similar moisture condition, between rainfall events. So one thing people have also looked at is something called runoff boxes. And this is 2 steps removed from actually field scale stuff, but it allows you to look at an unlimited number of treatments and replicates because you can do it in a undercover, in a building or in a greenhouse or something. So here's what the apparatus looks like, and there's a National Phosphorus Research Project group, and they came up with a standard size and shape and everything of a runoff box so that they're all looking at things with the same kind of apparatus. So it's always 20 centimeters wide. It's always 5 centimeters high at the bottom, 7.5 at the top. It's always 100 centimeters long. And basically you put in your various soils and treatments. You can adjust the slope however you want, depending upon how much slope you deal with in your region. There are drainage holes in the bottom, and there is a gutter at the end to collect the runoff. So these are now used in several of the studies that I'm going to show you today, again, because they allow us to look at very many variables. We have to be very careful, though, about extrapolating stuff in a packed box back to the universe. It can give us some differences among treatments, but it doesn't necessarily exactly quantify what might go on in the field. So I just want to caution you about that. Okay, so one of the things people often want to know is phosphorus sources being equal and rates being the same, what are the losses? Is it the same regardless of source type, or are there differences between sources? And so again, the USDA Watershed Lab, and this particular study was led by Andrew Sharpley and Pete Kleinman. Pete Kleinman talked last year about the ditch drain project. They essentially looked at a control commercial fertilizer and 3 different manures, a poultry, a dairy, and a swine. They looked at both surface application and incorporation. They looked at 80 pound per acre phosphate rate, and their calculations was based on this is the amount of phosphate they believe would be applied in a nitrogen-based recommendation for corn silage at a pretty decent yield goal. And they looked at 3 soils and runoff boxes with simulated rainfall. Now, I'm only going to show you the data for the Hagerstown soil because that's a soil we also have in our state in the Limestone Valley. All right? So here's an example of the data from the surface application. Okay? They looked at both a low Hagerstown that have an FIV of 12 and a high Hagerstown FIV of 415, and this is the total phosphorus in the runoff, the total phosphorus. So they had a control, okay, low P soil, high P soil, no phosphorus added. Diammonium phosphate, low P soil, high P soil. Dairy manure, low P soil, high P soil. Poultry manure, low P soil, high P soil. And a swine manure, low P soil, high P soil. Same amount of phosphorus was applied in all of these treatments. And look at the differences. All right? Pretty substantial. What surprised me, I think, was the fact that the soils that had been fertilized had much more total P lost in the high soil than the control. And their explanation for this is as the rainfall hits the soils interact with the material you put on it and start absorbing things virtually immediately. So when you've wetted your soil and then looked at the runoff for 30 minutes, there's already been a lot of interaction of your phosphorus source in your soil, and the soils carry with them a lot of material that they picked up from the the phosphorus source that you applied. Now, the interesting thing here is, if you look at what's going on with the total phosphorus in the control where no P was added, it looks almost identical to the total P in the dairy litter treatment. Okay? Now, what we're going to look at next is the dissolved phosphorus, and we're going to see where the real story is here. Okay? This is the soluble phosphorus, the dissolved reactive phosphorus, or the dissolved phosphorus. And here you can see that it's not the same at all, that the dairy manure has led to much more soluble phosphorus on both the high and the low soils than the control soil did. And again, you can see that the amount of dissolved phosphorus that's coming from the high P soils, again, is intensely influenced by the source of phosphorus that was applied to those soils, because we're getting much more dissolved P in the soils that have had a phosphorus source applied to them than we're getting in the high P soil itself. And surprisingly enough, the dairy manure was the least in terms of the dissolved P losses. And one of the reasons for that is that there's a lot more stuff, a lot more material put on the soil, and essentially they believe that it absorbed a lot of the water that was applied to the soil. In this case, Wilson, everything was surface applied. Everything was left on the surface. They also have some data for the incorporated stuff, but their study didn't show the graphs for the dissolved portion, and I'm not showing it here. If you'd like that information, I can certainly send it to you. But this is surface application on a very low P soil and on a higher P soil of the Hagerstown Soil Map Unit. Okay? Okay. So one of the things that comes up in a lot of discussions is, well, I'm composting my material. How does that affect how phosphorus behaves? You know? And I think that's a perfectly valid question. There's more and more emphasis now on looking at alternative uses of manures rather than applying them in their raw or unaltered state. Composting is one of the things that's done to make the poultry litter less of an odor problem, more appealing to a wider audience, and it, of course, is a good source of organic matter in your soil, as well as being a source of nutrients. And it's commonly used by organic growers. So this is an important thing to look at. This was done by Vadas and Meisinger out at USDA. I believe Pete Vadas was out doing a postdoc then. They looked at runoff boxes at a 5% slope. They looked at the Mattapack silt loam. They got the soil from the Y, but the experiment was done over here. They put some corn residue on the surface. They put enough to mimic what a 100-bushel corn grain crop would leave. They looked at a 100-pound per acre phosphate rate. The FIV of the soils was 160, so it's already at a point where in Maryland we would have to run the phosphorus site index to add any more materials. And they had both a control, a poultry litter treatment that supplied 100 pounds of phosphate, and a composted poultry litter treatment. So the phosphorus inputs were the same in both materials. Okay? And again, this is in runoff. So first of all, they measured how much runoff they got in the 30 minutes of runoff. And you can see that there was less runoff from the control runoff boxes than there were from either the poultry litter or the composted poultry litter. So there's more water moving off in these treatments than there were in the control that got no phosphorus. Total suspended solids, this is the particulate that's coming off. Some in the control, but a lot more in the poultry litter and in the composted poultry litter. And understand that those suspended solids are probably from the nutrient material itself, all right? Not from the soil, but from the nutrient material itself. The total phosphorus leaving was very little in the control soil, despite the fact that this was a pretty fertile soil, right? Whereas the total phosphorus in the poultry litter was 26, and in the composted poultry litter was 17. So again, more total phosphorus and more total suspended solids in the treatments. But what about the dissolved phosphorus? Again, very, very little in the control. And this is measured in a weight unit. This is kilograms per hectare, so it's a weight of loss, right? Whereas the poultry litter was up about 7, almost 7, and the compost poultry litter was less than 3. Okay, so look at this. There's a lot of suspended solids coming off both these treatments, a little bit more in the poultry litter than in the composted poultry litter, but in terms of the soluble phosphorus that's coming off, there's way more in the poultry litter than there is in the composted poultry litter. And I've also given here, you hear the water extractable phosphorus. 25% of the phosphorus in the poultry litter was water extractable, whereas only 14% of the phosphorus in the composted poultry litter was water extractable. And this is one of a number of studies that support the fact that we may want to look not only at the total phosphorus in our materials when we're trying to assess the risk of loss, we may also want to look at the water extractable phosphorus, because that appears to give us more of the story here than just how much sediment we're losing and how much total phosphorus we're losing. Okay, the difference between 26 and 17 in total phosphorus is way different than the difference of almost 7 and not quite 3 in terms of dissolved phosphorus. Okay, I also want to talk about the long-term impacts of adding significant amounts of an organic material like compost. This has a tremendous amount of relevance to our organic producers who rely very heavily on organic sources like compost for nutrients. And it's a very interesting study that tells us that we need to not put our blinders on when we're trying to assess risk. And this was a study done at Virginia Tech's Northern Piedmont Ag Research and Education Center near Orange, Virginia. This is about the same latitude as St. Mary's County, and it's almost exactly opposite Fredericksburg, Virginia, and it's over in the Piedmont. So it's very typical of our Piedmont soils also. And they did their work with field plots, not runoff boxes. So it's much more realistic in terms of losses than runoff plots would be. And they did use rainfall simulation. They did the experiment on the dominant soil map unit of some vegetable experiments they'd been running. It's the Fauquier silty clay loam. It's a very deep, fine-textured, high P-fixing Piedmont soil. It has about 2 feet of an argillic horizon that has a high clay and a high iron oxide content. This soil is going to fix phosphorus till the cows come home. All right. They looked at the effect of 5 years of organic applications of materials at a nitrogen-based rate. All right, so these are pretty substantial, particularly for the composts. And they rototilled the material in, which is very conventional tillage. All right. Okay. First of all, I want to show you how much actual phosphorus and carbon they added over those 5 years, and also look at the Mehlich-3 soil test at the end of the experiment. They didn't add any phosphorus to the check. Over 5 years, they added 147 pounds of phosphate fertilizer, 723 pounds of phosphate in the poultry litter, and 2,159 pounds of phosphate in the composted poultry litter. Carbon additions, there was no carbon added in the check. There's no carbon added in the commercial fertilizer. There was about 5 tons of carbon added in the poultry litter treatment and about 34 tons of carbon added in the poultry litter compost treatment. All right. This was very infertile at the beginning. This is a 2-inch sample, not an 8-inch sample, but the Mehlich-3 at the end of the experiment in the control was 23. All right. Now that's almost equivalent to the FIV. All right. The commercial fertilizer parts per million after 5 years was 69. The poultry litter treatment was 77. And the poultry litter compost treatment was 247. So this has been enriched pretty significantly in terms of its soil test value. And that's not surprising considering that we've added over 2,100 pounds of phosphate. And you can see that there's about a 3 times difference here in terms of the amount of phosphate added in the compost versus the raw litter. And it's almost the same in terms of its impact on soil test levels. So, from which of these treatments would you expect the greatest particulate phosphorus loss. Which would you expect to have the greatest dissolved phosphorus loss? And which treatment do you think might be the greatest threat to water quality? Come on, some of you folks that have been really quiet and do this for a full-time job for extension need to throw your hat in the ring here. No, I'm going to have to start thinking about some remedial classes. Okay. Okay, Janie, let's look at the data. Okay. Now, this is the runoff data, and this is just the sediment and the different phosphorus forms, okay? Dissolved reactive phosphorus, 47 in the treatment that got no commercial fertilizer, or no phosphorus at all, 46 in the commercial fertilizer, no difference there, 51 in the poultry litter, and 38 in the poultry litter compost. Okay, so there's not a whole lot of difference here. All right, let's look at the particulate phosphorus. A lot of particulate phosphorus left the field in the soil that got no phosphorus at all, less in the one that got commercial fertilizer, and even less in the poultry litter, and least in the poultry litter compost. In terms of the amount of particulate that left, the most particulate left in the untreated check. Not too much difference between commercial fertilizer and poultry litter, but look how protective the compost treatments were of sediment leaving this field. Only 35 compared to almost 300 in the untreated, or neighborhood of 150 for the two intermediate treatments. All right. Now, I do want to tell you that this is weight per area, grams per hectare, kilograms per hectare. I do want to emphasize that the actual concentration of the dissolved reactive phosphorus in the poultry litter runoff was 9 milligrams per liter, as compared to 1.6 milligrams per liter in the compost. So it was richer in stuff, but less left the field, so the amount measured as a weight was much less. And there's a lot more to this story. Here's some what I'll call corollary data. They measured how much of the water actually infiltrated the soil. Remember, they knew exactly how much they put on. They gauged it. They measured how much ran off. And they measured how long it took before they got any runoff. All right? Okay? So for the infiltration, okay, the untreated, no phosphorus, 23 millimeters. Commercial fertilizer, a little bit more. Poultry litter, a little bit more infiltrated. And the poultry litter compost had tremendous amounts of the water infiltrating the soil rather than running off. All right. Runoff, 25, 20, not too big a difference. Poultry litter, a little bit less. Only 7 millimeters of the water that was put on those plots actually ran off. And the time to run off, 8 or 9 minutes, again about the same for no treatment versus commercial fertilizer. More time until you got runoff in the poultry litter, and almost a quarter of an hour until you got runoff in the poultry litter compost. Well, all things being equal, if this field had 3 different treatments in it, all right, it could rain a long time before the water would run off on the treatments that got the compost, the poultry litter compost, whereas rainfall would start to run off before 10 minutes in the plots that only got commercial fertilizer or that got no treatment at all. All right. So one of the things Greg Evangelos and John Spargo said in their study, and this was done by Greg Evangelos, who's still at Virginia Tech, and John Spargo, that's now running the lab at Penn State. They concur that significant additions of organic matter over a number of years can actually alter your physical properties of your soil, what we commonly call tilth, all right? And that can have a very important impact in terms of how nutrients like phosphorus leave the field, all right? They do want to warn that we have to be careful about extrapolating their findings to the universe. this this tendency to have the phosphorus move into the soil as opposed to move off the soil is very good if you're dealing with a deep, fine textured soil that has a high P fixing capacity, because any phosphorus that moves below the root zone is going to get fixed by that soil, particularly in the subsoil. They certainly are cautious about saying that this would be a good practice in a sandy soil with a high water table. All right. They did say that even though the phosphorus inputs were high in the composted treatment, we need to be careful about realizing that if things don't run off, they're going to infiltrate. Okay, it's not that it's going to go nowhere, but in a soil like this, where you've got this tremendous phosphorus fixing capacity, not only in the topsoil but in the subsoil, infiltration of phosphorus from that manure is not going to pose a water quality problem for many, many, many years, perhaps many decades. Okay, one more important thing I want to deal with, and then we'll say adios amigo, and that is this. I hear this a lot. I'll just stop applying my manure for a couple years. 4 or 5 years down the road, I'll be able to use it again. I'm afraid it's more than 4 or 5 years down the road. And I want to tell you about a study done here in Maryland, Frank Cole and Bob Cradaville. They actually induced high levels of soil test phosphorus by adding 200, 400, and 800 pounds of phosphate in manure for 3 years. And they did this in 3 different research centers: the Upper Marlboro Center, that's the Upper Coastal Plain, the Y on the Russell Bluffs of the Eastern Shore, and Poplar Hill. And the data that Bob Cradaville was willing to share with me is a decade long. There's several more years of data that haven't been analyzed yet, and they're continuing with this experiment. So this is the 800 pounds added over every year for 3 years, 600, 400, 200. And you can see that in 10 years, there's not been a whole lot of change. And this is just the Poplar Hill site, okay? Bounces around a little bit in here. Who knows why? They didn't hazard a guess. But certainly not massive change. All right. Similar results were found for the other 2 locations, and they're looking at both a pretty intensive corn, wheat, bean double crop, and they were also looking at a forage rotation. And you can see there isn't a whole lot of difference between the row crop and the forage in terms of the impact on soil test. This is 10 years of data, and I wouldn't say that we're seeing any massive changes yet. Okay. Now I want to show you just the high treatment. And again, this is 10 years. In the beginning, various levels from about 350 to 450, depending upon the site. After 10 years, we're only down to here. So by my estimates, we're about 400, 450 up here, down to about an average of 320 after 10 years. So the next time someone says, hey, I'll stop applying manure for a couple years and it'll go down, just remind them that after 10 years, we're still not seeing very significant drops. Yes, the soil test levels are declining, but they're certainly not declining very fast, nor can we expect them to. Okay, so here's our take-home messages. We actually are getting to the end here. Soil test P is plant available, and anybody that tells you it isn't has their head in the sand. All right? Once soil test levels are elevated, it's going to take many years, probably many decades, to bring them down again. Soils have a finite capacity to retain and fix phosphorus. They only have a certain amount of iron oxide. They only have a certain amount of surface on those iron oxides. And once those surfaces are filled, they're not going to be able to affix any more. All right? Any more that's added is going to stay in a labile form. It's going to be soluble in water. It's going to leach when it rains, and it's going to run off if water flows over the soil surface. All right? Improved tilth can lead to reduced P losses and runoff. All right? Okay. Questions or comments? Yes, I'll go back over to those slides. Sure. Oh, you'd like a PDF of them? You betcha. Craig, we'll have this whole set up on our website probably by tomorrow afternoon. You can print off whatever ones you want, and I'd be glad to send you individual ones if you'd like. I want to thank the people that gave me the slides. Frank Cole's grad student, John White, shared his runoff at SEMREC with me. Frank Cole shared the work with me from that he and Jennifer Butler did. Bob Credival shared the slides about the drawdown. So I was able to show you a lot of very, very useful data from Maryland sources. And if you have any other questions, please ask away.